Hello, welcome to Module 3, Video A. Today we're going to be talking all about linear regression. So first of all, what is it? Well, linear regression is a way to model data, specifically data with linear correlation. So what I usually think of is fitting a line. So these are some very arbitrary data points. But we've got data points here along the x. For every x, there's a certain height in y. And what linear regression does is it draws the best line that it can between these data points. It's going to draw the line that minimizes the distance between each data point and the line. Specifically today, we're going to be talking about multilinear regression. So that is when you are using several predictor variables to predict your response. So in our notation here, our response variable, what we're trying to predict, is usually denoted as y, and then our x1, x2, x3, and so on are our predictor variables. So for example, say we're trying to predict the growth rate of our tree. So growth rate right here is y. Our beta naught, that's our intercept, so that would kind of be like the average growth rate of all trees. What we would do is a blind guess. And then we're going to add to that the effects of all our other predictor variables. So perhaps x1 is the amount of water that the tree receives. So beta 1, which is its coefficient, is maybe going to be positive. Maybe the more water it receives, the better it grows. Then over here, beta 2, and we have beta 2 and x2, so maybe x2 is how much, maybe that's temperature. So perhaps this one might have, maybe a negative coefficient. It gets too hot, then the tree doesn't grow as well. So on and so forth. And that's kind of the basics there. Linear regression can be a really powerful tool, specifically when a few different conditions are met. And those are the conditions I have listed right here below. So the first condition is that the relationship between the response and the predictor variables is linear. We're fitting it with a line. If the relationship isn't linear, linear regression isn't going to do too well on it. One of the next assumptions is that there's independency and normality of errors. So this is all about the distribution of your data and how your data was collected. Was it collected in a way that all the data points are independent? And also, do we have a good distribution, or do we have like a bunch of really high points and then a few low points? Do we have skew going on? And then the third is no multilinearity. That's about how much the predictor variables are correlated with each other, and we'll get into that a little more later. But kind of the main takeaways here is that when our data has linear relationships and when we've got a good distribution of it, linear regression does extremely well. In fact, if these assumptions are met, it has been proved to be the best model. And that's really awesome. So that's why we'll be looking at it. Sometimes we're not going to perfectly match all of these assumptions, but if we can match some of them, we can still get a really good model. And just before we go on, a few other benefits of linear regression. One of them is, it spits out a formula. So once we've performed our linear regression, we can go back and we can look, oh, hey, this is exactly how predictor 1 is affecting things. This is exactly how predictor 2 is affecting things. That's really powerful. And also just that it's computationally simple. The math behind it is quick and it's reliable. So that's why we love linear regression, and we'll be getting more into it.